And then we would switch the left and right hand sides too, but that's a minor issue, right? So this is just a slightly different form of writing the same equation, just putting everything on one side. And now you see that the case of tangent planes of graphs of functions in two variable can be thought of in two different ways. Okay? Namely, you can think that you started with a function in two variables and you just look at the graph and you look at the tangent plane. But you can also think of it as a special case of the more general case of functions in three variables, except you take as a function in three variables this very special form, f of x y minus z. Either way you approach it, you get the same answer. But now you can appreciate more the connection between this answer and this. Many people ask me after last lecture why when we look at the equation of the tangent line of function in two variables, it's as though we are dropping this term, z minus z0. So there's this negative 1 in the, which we just draw. Well, geometrically it's clear. In fact, the board stayed since Tuesday. I guess nobody likes this little small board, except for me, which is good. So this is the tangent line, and this tangent line corresponds along this tangent line to the level curve. We have the same value of z equals z0. So that's why we drop this term to go from this equation to this. So you can get this equation from this by dropping z minus z0, because z is equal to z0 along the level curve. But also you can now understand that this formula is a special case of the formula for the tangent plane to a general level surface, which actually looks like this one. Except we have a third variable. In the special case, when the function is like this third term becomes extremely simple. It just gets a coefficient negative 1, so you just get minus z minus z0. Okay? And to make the analogy complete, let's actually look at let's fill in this square. You know, it's like when you do IQ tests. I've never done it, by the way. But I know it's easy to find them online. And I think the problem is often like fill in the square. So this is exactly the kind of question here. What should be here, right? In other words, this is the case of three variables, and this is a special case of that, right? Now, what's the analogous special case for functions in two variables? That's the case when this function of two variables, special case, when this f of xy is some function in one variable, let's call it g of x minus y. And so you see in this case, in fact, you know what I'm going to do to make it look more like an analogy. Let's reposition the boards. There we go. So now I think it's more clear what I mean by filling in a square. I want to find a special case of this, which is analogous to how we found the special case of three variables, and that's the case when now our function in two variables is equal to another function in one variable minus y. Okay? In this case, the equation f of xy equals 0 means y equals g of x. Right? And this is a graph of the function g of x. So a level curve for a function of two variables can become the graph of a function in one variable when this function in two variables has a special form. Did you have a question? Good question. So what would happen if we put some k? Right? If we put some k, then it would be here minus k. I would put minus k. Right? So then I could just absorb k into the definition of the function g of x. If I redefine my function g of x by subtracting k, then I would get back the level 0. So that's why we don't lose any generality by looking at the case of level 0 rather than as opposed to general case. So let's just look at the case of level 0. Okay, so that's a graph. And so now this formula for the tangent line, note that f sub x of xy now is g prime of x. Just like here, the partial derivatives of the big function f with respect to x and y were just the derivatives of the small f. And now the role of the small f is played by g, so the partial derivative like this is just g prime, and the partial derivative with respect to the second variable is negative 1 again. Because this minus y now plays the same role as minus z played here. So when we take the derivative, we get negative 1. So now this formula for the tangent line becomes g prime of x 0 times x minus x 0 minus y 0 equals 0. Let me rewrite this. This is equivalent to saying y is equal to f prime of x 0 times x minus x 0 plus y 0. We recover the old formula for the equation of the tangent line to the graph of function in one variable. That formula is exactly this one, right? The slope is f prime, you multiply x minus x 0, and you add the value of the function at the point x0, which is y0, right? So there's nothing mysterious in these formulas. In the special case, we get back the old formula we've known all along. And also, this now sheds some new light on this coefficient negative 1, which many of you have found mysterious. It's not mysterious, it's as mysterious as this coefficient negative 1, which shows up in the old formula for the tangent line to the graph. We were not surprised to write the formula for the graph of the function is y equals f prime times, in this form. But if you have it in this form, you can rewrite it like this. And when you write it like this, you find the coefficient negative 1. That's exactly the reason it appears is the same reason why this negative 1 appears. Okay? Any questions about this? Yes. Why do we choose a special case? That's a very good question. Why do we even choose a special case? Well, from the point of view, let's talk about this case. From the point of view of functions in two variables, this sounds strange. Why would you write it like this and not f of x minus xy or something, right? So from the point of view of functions of two variables, it doesn't make any sense. It makes a lot of sense, however, from the point of view of the theory of functions in one variable. When we study functions in one variable, we would like to visualize them by graphs. Right? When we draw a graph of function in one variable, we introduce one more variable, and we look at the graph, which is y equals f of x. What I'm saying now is that within this formalism that we are developing, we can think of the graph of g of x, which normally we would write as y equals g of x. Just in this form. And when we write it in this form, we never say the word level curve or anything like this, we just say graph. But we have to realize, it's important to realize, to see the connection between different formulas. It's important to realize that this graph actually can be thought of as a level curve for a function in two variables. And that function just happens to be this function, even though it looks kind of, there's no reason a priori to study such functions. We have introduced them because we started from the point of view of functions in one variable, and then this will naturally fill out once we started to look at the graphs. So that's likewise in this case. Okay, yes? That's right. It could be a point or finitely many points. Because you could be, let's look at the function. And for good reason, right? If the dimension of the level curve is going to be the number of variables or level curve, level surface, and so on, will be the number of variables involved minus 1. If you have 2 variables, it's a level curve, so dimension 1. If you have 3 variables, it's a level surface, dimension 2. If it's a function 1 variable, it will be a dimension 0. And 0-dimensional objects are just collections of points. And the way it works is just like this. Let's look at, for example, if you have a parabola. The level curve consists of 2 points. But if you have a cubic parabola like this, there will be 3 points. And if you have a cosine, you will actually have infinite many points. Infinite many points if the level is between 0 and 1 and -1. And if the level is higher than 1 or lower than -1, then it will be empty. Level curve will be empty, or level surface. In this case, it's sort of level point. We don't have a good word for a collection of points. So it's like zero-dimensional object, manifold, as a mathematician would call it. Any other questions about this? Yes?
One in one box, you have G prime that's 0, and then the other one you have F in two boxes.
Oh, yes, I'm sorry. Thank you. That was a mistake. Thank you. Yeah, it's G prime, of course. I mean, I'm just saying this formula becomes this formula. But I call it G, right. Sorry, yeah, I completely messed it up. Right, good job. Okay, so that will do it for us in this topic, and actually we're running out of time, so we need to talk about something else today also. I really wanted to go over this slowly to emphasize the connection between these different objects, because I think that there are different dimensions, different number of variables at play, and it could be very confusing. But I think that if you put this in this sort of in this picture where you have these 4 squares, 2 variable case, 3 variable case, special case, and 2 variable special case, and 3 variables, then I think it becomes much more clear. All right. But the next topic we'll discuss is concerns finding maximum and minimum of functions. And as is always the case, it's actually instructive to look at this question already in the one-dimensional, in one variable case, because we already can gain some insights into the problem by looking at this very special, the simplest possible case. If you have a function in one variable, it's a natural question to ask where this function attains maximum and minimum values. That's important because this function could correspond to something in real life, and you may want to maximize that or minimize that. And so the first point I want to emphasize is that there are 2 different types of maximum and minima: the local and the global, or the global ones are called absolute. But I like to think local global. I like this terminology a little bit better. So what do I mean by local? So let me draw this. For a function one variable, it is very convenient to analyze everything by using graphs of functions. And graphs again are curves on the plane, right? So we introduce a new variable y, and we write the graph as given by the equation y equals f of x. So let's look at this. Let's look at this kind of function. That's a very typical example. So I want to focus on this point. So clearly, this point, the value of the function at this point, so this would be the point x0, and that's the value of the function. This is f of x0. The value of this function at this point is greater than the value at nearby points. So that's an example of local maximum. A point is a local maximum if there is a small neighborhood of this point, such that if you restrict your function to this neighborhood, which is this little interval in this case, then this will be the maximum value on the interval. Okay? But is it a global maximum? Clearly not, because I have a point here, for example, x1, for which the value is higher. So that's not a global maximum. That's not a global maximum either. In fact, in this example, there is no global maximum, because I'm assuming the function keeps growing, keeps increasing, as x is increasing. Okay? If that's the case, there is no global maximum. So global maximum is a completely different, finding global maximum is a completely different game than finding local maximum. Finding local maximum just involves analyzing a function on a very small interval around this point. Finding global one sort of involves analyzing all points in your domain. The way I phrased the question so far is as though we were studying global maximum on the entire line, on the entire x line. Okay? And you see clearly that question often doesn't have an answer. In other words, there is no global maximum. Simply because for any point there will be another point which will have a higher value, and so on. Okay? So the question of finding global maxima, it is better to phrase on domains which are bounded, not on the entire line, but on bounded domains. Bounded means that it's finite. So it's better to say what is the maximum of this function on this interval. Okay? This is an example of a closed bounded domain in the following sense. First of all, it's bounded because it's finite. It doesn't go to infinity. Second, it is closed because it contains the endpoints. And these are the kind of domains that we should look at if we want to ask questions about global maximum or absolute maximum and minimum. So let's look at this question in this particular case. In this particular case, we see that the maximum value is actually taken at this point. This is the maximum. So now you can appreciate why you have to include the endpoint. If we did not include the endpoint, there wouldn't be a maximum, because no matter how close you are to this point, there will be another point even closer for which the value will be even higher. So therefore, there will be no maximum. Right? So in order to guarantee that you have a positive answer to the question of existence of maximum or minimum for that matter, you should really look at closed and bounded intervals. And then what happens is that the maximum can be attained either at the boundary, which is the case here, or it could be some local maximum which lies in the interior of this interval. In this particular case, you do have a candidate. You do have a candidate for a maximum, this one, because it is a local maximum and it is within this interval. But it's not a global maximum on this interval because the value of this function is just bigger. But if I were to take a different interval, if I were to take an interval like this, for example, okay, then this guy would win, because at the boundary the value would be smaller. You see, at the boundary the value would be smaller, so this guy would have the highest possible value on this interval. So the bottom line, the upshot of all this, is that the absolute maximum can be found in a finite set of points. And those points are, first of all, the endpoints, and all the points where you have potentially local maximum minimum. So the global maximum on the interval, on a bounded interval, on a closed interval, a bounded interval, let's call it AB, can be found maximum of some function f at one of the following points. One of the following points. The endpoints, which are a, b, and the points of potential local maximum. And here it's important to emphasize the word potential. And those are the points for which f prime of x is 0. Because certainly, if it's a point of local maximum, then the slope of the tangent line at this point is going to be 0, right? Because if you have a non-zero slope, you just move away from this point, and you'll get a bigger or smaller value. On one side bigger, and on the other side smaller. So the only way you can have possibly have a local maximum is to have slope 0. A slope is a derivative, so that's why these are the points for which the derivative is equal to 0. Okay, so this is the first statement that I want you to remember, or remember from the recall perhaps from the Multivariable calculus, which is that if you're looking for global maximum, what you need to do is simply measure or evaluate the value of the function at the endpoints. Evaluate this point, evaluate this point. Next, find all the points where the derivative is 0 and evaluate the function. So you get a finite list, and then just pick the one or the ones where the value is maximal. These are the values. These are the maxima of this function on this interval. In other words, you don't have to look through all the points on the interval; they're infinitely many, but you only look at the endpoints and the points where f prime is equal to 0. That's the algorithm for finding maxima of a function. And likewise for minima, just replace the word minimum by maximum by minimum. So it's exactly the same. Now, so before I go and generalize it to the case of two variables, I want to explain what I mean by the word potentially, potential local maximum. In other words, if the point x is a local maximum or minimum, then the derivative is 0. I will explain this because the slope has to be 0. If it's a maximum, minimum, slope has to be 0. If the slope is non-zero, it means you can increase or decrease the value by moving a little bit away from the point. So this is true, but this is not true. This is not true. In other words, if the derivative of your function at your point is 0, it doesn't mean it's an absolute maximum or minimum. And the reason is the following. The reason for that is the following. There's a very simple counterexample to this, namely function x cubed. So f of x is x cubed, f prime is 3x squared, and so f prime of 0 is 0. Which we see, right? We do see that the slope at 0 is 0, right? But is it the point of a local maximum or minimum? It's not, because if you go this way, it increases, and if you go that way, it decreases, right? And in fact, if you think in terms of monomials, the same thing will happen if you have x to the odd, to the n where n is odd, like 3, 5, 7, and so on. Because the derivative of x to the n is n times x n minus 1, so it's always 0 for this function. But if n is odd, then for positive x, this value is positive, and for negative x, it's negative. So it's going to look like this. But if x is, if you have y to the n where n is even, so it's 2, 4, and so on, then it's going to look like this instead. And so in that case, it is okay. It is actually a point of local maximum, minimum. Local maximum in this case, and if it were negative, it would be local. Sorry, this is minimum, but if it were like this, it would be maximum. So in other words, there are many possible scenarios where you have a derivative equals 0, and it is a maximum, and there are many scenarios where the derivative is 0, but it's not a maximum or minimum. Okay? So it only goes this way. If it is maximum or minimum, then the derivative is 0. That's why I said those are the points which potentially could be maximum or minimum. Okay? So in principle, you could rule some of them out from the outset by saying, well, these points are actually f prime is 0, but the point is not maximum minimum. So then it cannot possibly contribute to the list of suspicious points or candidates for global maximum minimum. But I think it's just much easier to just take all of them, because it's going to be finitely many, and just evaluate your function f at all of them, and then compare. Where do you get the largest value, or where do you get the smallest value? You guys following this? Okay, good. So that's why the way I formulated this, I didn't want to, at this level, to try to differentiate between the ones which are actually maximum and minimum and which are not. I just said, let's look at all which are potentially maximum and minimum. Okay, so that's the one-dimensional case. And now, in some sense, we already know everything we need to know, because in the two-dimensional case, it's going to look exactly the same. The criterion will be slightly more complicated. Maybe I'll say one more thing, which is that there is a criterion to see whether the function is a maximum or minimum in this case. Namely, suppose that f prime is 0, but f double prime at this point. Let me emphasize that it's a particular point x0, which was the point 0 in my previous example. Let's call it x0. This is positive. Then it's a maximum. It's a minimum, sorry, minimum, local minimum. And if